Hi everyone. A few weeks ago, Amazon Web Services had a massive outage that took down a lot of services. They have finally released an official summary of what went wrong in US East 1, their loudest region in Virginia. In this video, we'll break down the root causes, but first, let's quickly review how redundancy works in the cloud. AWS has data centers around the world. A group of data centers is called an availability zone or AZ. A group of AZs is called a region. When you deploy to a region, AWS can run your service in multiple AZs. If one AZ is down, your service is still up and running in other AZs. At a high level, if you deploy to multiple regions and one region is down, let's say US East 1 in this case, your service is still up and running in other regions. So you may ask, why did not affected companies use multi-region setup? Because it's expensive. Not just in money, but also in engineering complexity. For many companies, being down half a day may actually cost way less than trying to maintain 100% uptime, which is close to impossible. Now, with this background knowledge, let's dive into what actually happened. According to AWS, the outage began just before midnight on October 19 and ended at 2 p.m. on October 20. They identified three major periods of impact. Let's talk about the first one. Between 11:48 p.m. and 2:40 a.m., DynamoDB, AWS NoSQL database, experienced increased API error rates. Essentially, customer services could not connect to DynamoDB, and the root cause is a race condition in its DNS management system, which maintains hundreds of thousands of DNS records that allow the service to run a large fleet of load balancers in each region. The DNS management system has two components. The first component, the planner, checks the health and capacity of the load balancers and periodically create a new DNS plan for DynamoDB endpoints. The second component, the enactor, actually picks up and applies those plans via Route 53. For resiliency, they have multiple enactors running across AZs. Under normal operations, the enactor picks up the latest plan, let's call it P1, and working through the API endpoints to apply this plan. This process typically completes pretty fast to keep the DNS state freshly updated. Before it begins to apply a new plan, the enactor also makes a one-time check to make sure that its plan is newer than the previously applied plan. As the enactor makes its way through the list of endpoints, let's say we have 10 endpoints here, it may encounter some delays. In these cases, the enactor will keep retrying until it succeeds for all endpoints. While this enactor is slowly working through all the endpoints, the planner generates a new plan, let's call it P2, and another enactor picks it up and applies through all the endpoints rapidly. It then starts its cleanup process, which identifies and deletes plans that are older than the plans that it just applied. At the exact same time, the first enactor, which had been unusually delayed, applied P1 to the endpoints, overwriting P2. The second enactor's cleanup process then deletes P1 because it's older than P2. As P1, the one and only active plan in Route 53 is deleted. All IP addresses of the regional endpoint of DynamoDB are removed. So the system has nothing to set up a connection for external customer services. The system could not fix itself automatically because the active plan was gone. This situation requires manual intervention to correct. As you can see, the algorithm for keeping DNS records fresh is problematic because it allows an older plan to override a newer plan. The one-time check that they did at the beginning of the transaction should actually be applied multiple times throughout the whole transaction. AWS phrase, "This process typically completes rapidly," kinda implies to me that they did not anticipate slow or delayed enactors, which is surprising to me because delays are very common in distributed systems. And because of that, an unusual delay breaks the whole system. This is just the first of 3 impact periods. I will cover the rest in the next video. If you enjoyed this breakdown and want more software engineering deep dives, please like and subscribe. Thanks for watching.